In this video I'm going to look at centres of mass questions from M2, but only the last part of the question. The bit where you've already found the centre of mass and then you suspend the object from one of the corners and you need to find the angle between one of the lines within the shape and usually the vertical. We'll start by looking at this question from the summer 2012 paper, but we'll also look at some 3D questions as well. So here we've got a plane lamina, and in previous parts of the question we already found out that the centre of mass has coordinates of 2.32 minus 3.6. I mark this centre of mass on the diagram and put it in approximately the right place. So if this is 8 units across, 2.32 should be somewhere within this rectangle around about here, and then minus 3.6 units down. I suppose actually it would be further down here, but actually as long as it's in this rectangle it looks roughly right. It doesn't actually matter, but it will help if it's roughly to scale. So I'm going to add a vertical line depending on where I'm suspending the shape. In this particular question then, it says that the shape is suspended from corner B and hangs in equilibrium. So suspending from corner B, and the angle between BD and the vertical. The vertical will go through corner B and through the centre of mass. We don't need to redraw the diagram with the centre of mass positioned on our page looking like it's below B. All we need to do is draw a vertical line going from B through the centre of mass. So I've drawn my line through B, through the centre of mass, and I want the angle between this line and the line BD, which is highlighted here. So the angle I want is this one, which I've labelled theta. Now from here it should be straightforward, especially in a 2D question, because we can make a right angle triangle and just use SOHCAHTOA. Creating a right angle triangle should be very easy. We've got two perpendicular axes, so we just need to create a line that's parallel to each axis. So we've got BD, which is parallel to the x-axis, and here's our line now, which is parallel to the y-axis. That means we have a right angle at this point here. So I've managed to create a right angle triangle, and we can see here we've got 3 sides of this right angle triangle. If we can just find 2 of the sides, then we'll be able to use SOHCAHTOA to find the missing angle. Now I think then we should be able to find the length of this side here and this side here. And indeed we can. This is 12 plus this little width here, which is 2.32. And then going down here we've got this height of 6 plus this distance of 3.6, which we take from this y coordinate. So we've got, this is our opposite side over here, which is the 6.36, so we've got 9.6 for this side, and then on our adjacent side we've got the 12 plus 2.32, so that's 14.32. So tan of theta is opposite over adjacent, so tan theta is 9.6 over 14.32, so theta is the inverse tan of this angle. And then I would round my answer to 3 significant figures in degrees. So now let's take a look at a 3D question. So here's a question from an older paper. This is from the summer of 2005. And this is actually question 3 part 3. The previous one, sorry, I lied there, that was actually question, I think it was 3 part A part 2, something else. Anyway, hopefully you already found that. So, on this question, in the first part of the question it's 2D. We've got a plane lamina, and then these are some kind of rods or wires or something here. So it's just the thin parts here. These are not making a solid shape. So we've got the plane lamina and then these wire parts here. And then these rods, yes, they're rods, these are kind of bent downwards so that they're sort of folded down, so this part here gets folded down and is like this. So this GF is perpendicular to the XY plane, and BE is perpendicular to the XY plane, and EF is now parallel to the XY plane. So if you think of the XY plane as being horizontal, imagine this is like a table or something, then these are now going in the direction that table legs would go. And in the same way, these rods here are bent over as well, so they drop down, so we've got J below D and we've got I below H. Now, I actually find these quite okay to deal with and to see what's going on, but a lot of people have trouble actually picturing what's happening here. It might be an idea to imagine looking at the shape from the top, so make a kind of bird's eye view or a plan view of the diagram when considering the different coordinates. Now, the X, Y and Z coordinates, finding those, this is something I'm going to assume that you've been able to do. So you've already got the X, Y and Z coordinates. It's probably worth noticing that in this question, by symmetry, the X and Y coordinates will be the same because the centre of mass would lie on this line of symmetry, which is the line Y equals X. And because these two parts with the rods have been folded over in the same way, the X and Y coordinates would still be the same, but we'd introduce a Z coordinate. And the Z coordinate ought to be negative because the centre of mass was on the plane, the XY plane, and it's now moved downwards. Now, it's been worked out in the previous part of the question then. The X coordinate and also the Y coordinate is about 2.2 and the Z coordinate is minus 4/7. So our centre of mass is on this line from A to C, but then we drop down vertically to get it just here. So the Z coordinate tells us this distance from AC down to here, and we need to create a right angle triangle, and we can also fill in our vertical. In this particular question, we're going to suspend the object from A, and we want the angle between AC and the vertical, which is going to go through A and through the centre of mass, and the angle we'll want will be the one in between. So if we suspend the object from A, we'll get our vertical line going through A and through the centre of mass. So just like before, we want to create a right angle triangle. So we want two things that are perpendicular. Now the Z-axis is perpendicular to the XY plane. So what we can actually do here is take a line going through the centre of mass and joining the line AC, and this will actually create a right angle which will be in between the line through AC and this vertical line. So here's the right angle triangle, and the right angle is here in between AC and the vertical, which is parallel to the Z-axis. The angle that we're looking for is alpha, which is over here. Now, in the previous part of the question, the distance was worked out. That was the distance of the centre of mass from the origin. So the distance of the centre of mass from the origin, which is the hypotenuse of our right angle triangle. So we're nearly there. It's just SOHCAHTOA again. We've got the angle, we've got the hypotenuse, and in this case we've got this length because this is just the Z coordinate, so we've got a length of 4/7 on this side. So we've got an opposite and we've got a hypotenuse. So here then we just finally finish up by saying that sine alpha is opposite, which is 4/7, the Z coordinate, or the modulus of the Z coordinate anyway, divided by 3.18, which is the hypotenuse, and we'll actually use the exact value. So if this has been stored in your calculator, or leave it as a surd and a fraction and use that value, and then we'll take alpha is the inverse sine of this, and we'll round the answer to 3 significant figures and give our units, which will be degrees, as that's what we were asked for.